In this week's experiment, you'll be looking at a variety of different chemical reactions, and you'll be writing chemical equations to explain what you see. There is lots of assistance for you in your prac manual, so make sure you make the most of this assistance. In the first section, we're looking at the acid-base properties of salts. We do this by collecting a small volume of the salt in question, and then add 2 drops of universal indicator to that solution. The universal indicator will cause the solution to change colour depending on the pH. We then compare that to a colour comparator chart, and that gives us a reading on pH. In this case, a pH of around 8 to 8.5. So how does this work? When looking at the acid-base properties of salts, first of all remember that the only species that determine pH of solution are hydrogen ions, or H3O+, hydronium ions, and hydroxide ions. If neither of those are being formed in solution, you're not changing the pH. Also remember that group 1 and 2 metals, things like sodium, potassium, magnesium, have negligible acid-base properties, and the conjugate base of a strong acid also has negligible acid-base properties. For example, chloride, nitrate, bromide. Every time you write a reaction, you're either going to be showing a salt breaking up to form cations and anions. You'll show an acid reacting to form hydrogen ions and its conjugate base. Choose your arrows depending on whether it's strong or weak. And for a base, we show it taking a proton from water. Choose your arrows, and it will be producing hydroxide ions and its conjugate acid. You will always be using one or more of those 3 equations to describe the acid-base properties of your solution. For the example we've just seen in the lab, sodium acetate, what happens when you put this salt into solution? It dissociates, breaking up into sodium ions and acetate ions. We then consider the acid-base properties of each of the 2 species. Sodium is a group 1 metal, no acid-base properties there. The acetate ion, however, is a weak base, so we can show that. Show it reacting with water, weak base, reversible arrows, and it will produce its conjugate acid and hydroxide ions. The presence of hydroxide ions means this solution will be basic. Another example to consider, I have ammonium chloride. It's another salt, show it breaking up into cations and anions. Let's look at the chloride ion first. Chloride is the conjugate base of hydrochloric acid. If hydrochloric acid is strong, chloride is negligible. The ammonium ion, however, is a weak acid. Show it working as that weak acid. Reversible arrows to produce its conjugate base and hydrogen ions. The hydrogen ions make the solution acidic. Finally, sodium chloride. I know you know it's a salt. Dissociates, breaks up into cations and anions. Sodium's in group 1. That has no acid-base properties. Chloride, the conjugate base of a strong acid, no acid-base properties. The sodium doesn't do anything. The chloride doesn't do anything. That solution must be neutral. You will have some salts which have both acidic and basic properties. The Ka and Kb values of these different ions will determine whether the salt will be acidic, neutral, or basic, and you can find supporting Ka and Kb values in your textbook. Moving on to section B of the experiment, I'm now going to do an example flow diagram for you, much like the one in your experiment, only not as long. I'm going to take a small quantity of silver nitrate, and I'm going to add a drop of sodium chloride to that silver nitrate. Yeah, well, by observation, you can see the formation of a cloudy white precipitate. Now, for your flow diagram for writing the reactions, you do have some assistance in your manual. You have a lot of data to support your observations. So for our first example, adding sodium chloride to silver nitrate, we notice a precipitate forms. So we can write a chemical reaction to show that. Silver nitrate plus sodium chloride. The precipitate we expect to be silver chloride. Chlorides are soluble unless you mix them with silver, mercury, or lead. So the combination of silver and chloride produces solid silver chloride. If you're looking for assistance, you could have looked at your table of data and you would find that the solubility product of silver chloride is 1.6 by 10 to the minus 10, very small. This means that silver chloride is insoluble and will form a precipitate. Next in our flow diagram, we are adding a small amount of ammonia to our silver chloride precipitate. And you can see that as we add the ammonia, the cloudiness disappears, the precipitate redissolves. So, upon addition of ammonia, the precipitate disappears. The fact that the ammonia has made the precipitate disappear means the ammonia must be reacting with that precipitate. So you can write your reaction, and again, if you use your page of data for assistance, you'll find the presence of a silver ammonia complex. That complex ion has a charge, which makes it soluble. And again, you use that table of data, you use that formation constant, Kf, to support the formation of this soluble complex. If you use that data to support you all the way through this section of the experiment, you should be very successful in writing your chemical reactions. Moving on to section C, We're now taking a variety of different metal nitrate solutions and then adding hydroxide to them. In this case, I've got zinc nitrate, and upon the addition of a drop of sodium hydroxide, you can see that we get a precipitate, an almost colorless, slightly cloudy gelatinous precipitate. To understand this reaction, we need to understand complex ions. Zinc nitrate, when you put it in water, dissociates to form zinc ions and nitrate ions. Those positively charged zinc ions immediately attract the polar water molecules. Zinc will attract 4 water molecules to surround it and form what we call a zinc complex ion. So we have a central zinc with 4 waters surrounding it. These surrounding water molecules are called ligands. And the combination of these generates a complex ion with an overall charge of +2. 4 neutral waters plus the central zinc in the middle, that's a total of 2+. This is our complex ion. Charged complex ions tend to be soluble in solution. Now we're adding sodium hydroxide to that complex ion. Sodium hydroxide produces sodium ions and hydroxide ions. First, the sodium ion, that is not going to want to approach the positively charged zinc, so that doesn't interact with the complex. Hydroxide ions, however, are negatively charged. They are attracted to the positive zinc, so we have the ability to use hydroxides as part of our complex ion as well. These hydroxide ions have the ability to work as a ligand. When we add sodium hydroxide, the hydroxide ion may replace a water ligand, and in doing so change the charge on the complex ion. The first addition drops the charge to +1, the second addition drops the charge to 0, and this neutral point is important. Neutral complex ions are quite often insoluble and form a precipitate. Back into the lab, if we then add excess hydroxide, in some cases, zinc being an example of one, you see that we can redissolve that precipitate. We now have a clear colorless solution again. How does this work? Adding excess hydroxide means that we replace even more water ligands with hydroxide ligands. As we do that, the charge becomes -1 and then -2. The reformation of a charge means that once again this complex ion will be soluble in solution. I'm now doing a similar experiment, starting with zinc nitrate once again, but this time instead of using sodium hydroxide, I'm going to add some ammonia. Once again, upon the addition of that first drop of ammonia, you'll see that we get a cloudy precipitate that looks very similar to last time. So with our same theoretical setup, ammonia is a weak base, which means it dissociates partially to give ammonium ions and hydroxide ions. Once again, those positively charged ammonium ions aren't going to want to approach the zinc. Hydroxide, we know, has the ability to work as a ligand, but looking on the other side of the equation, ammonia will also quite happily work as a ligand. Like water, it is a polar molecule. So adding ammonia, how could we see a precipitate? It must be due to the hydroxide ions. Replacing water ligands, they are the only ions that have the ability to drop the charge. Remember, we need to get down to a neutral charge in order to see a precipitate. We write this complex ion in text just with zinc, 2 water and 2 hydroxide, as shown here in blue. If we add excess ammonia, you see that we can redissolve that precipitate. Now, how might this precipitate redissolve? If we add excess ammonia, we're adding ammonia and hydroxide, but ammonia being a weak base, we are adding predominantly ammonia molecules. So what often happens is the ammonia can replace all of the ligands surrounding the central zinc. We end up forming a positively charged species again, which means that once again our complex is soluble, and we can show that complex like so, once again shown in blue. So bear these rules in mind when you're working with complex ions and ligands. Charged complexes tend to be soluble, neutral complexes tend to form a precipitate, and it is the combination of the metal and the ligand that tends to determine the color of a complex. If you see a change in color, most likely you're seeing a change of ligand. Moving on to the final part of your experiment, looking at some redox reactions, I'm going to start with the example system from your experiment. We're going to add some potassium dichromate to a test tube, then going to add some sulfuric acid, and then going to add some iron sulfate, drop by drop, and watch what happens. As we add, you can see the solution go from the orangey yellowy colour through to a light green. Now, how do we go about writing reactions to show this? We're mixing potassium dichromate, sulfuric acid, and iron sulfate. Really, that's just like mixing dichromate, acid, and iron 2+. Find them in your list of standard reduction equations that we've given you in your prac manual. Note that each half reaction is already balanced, so you don't need to use the ion electron method in this experiment. You can simply take the reactions straight off your table of standard reduction reactions. The chemicals we've added provided everything we need for the two half reactions. So for a spontaneous reaction, we need one of these reactions to occur as written, reduction, and we need another to occur in the reverse direction. We need an oxidation reaction. We have the dichromate and acid, which is what we require in order to get the blue reaction to proceed in the forwards direction. And we have the iron 2+ that we need to get our oxidation reaction to occur, the red reaction, in the reverse direction. We can also see that if we calculate E0 cell, our cell potential, which is calculated by taking the reduction potential of the reduction reaction and subtracting the potential of the oxidation reaction, so reduction minus oxidation, we would get a positive number for this, which tells us that this reaction will occur, will be spontaneous. In order to add these two reactions together to get an overall equation, we need to make sure that the number of electrons in each reaction balance. We can't have electrons being created or destroyed. We can do that by multiplying each half reaction by a number that will ensure that we get the same number of electrons in both reactions. In this case, the easiest way is to multiply the iron reaction by 6. Now both reactions have 6 electrons. We can now add the two reactions together. The electrons should cancel out, and you'll sometimes find water and hydrogen ions cancelling out as well. And once you combine these two and have cancelled everything out, you'll have your overall redox reaction. So now that we've had a look at some test tube redox reactions, we're going to have a look at an electrochemical cell, at a galvanic cell. We're going to take a redox reaction and split it into its two respective half cells. This will allow us to observe how each half cell behaves, and we'll be able to measure the cell potential of the redox reaction. Start by taking the two metal electrodes that you'll be using. In this experiment, one will be copper and the other will be either silver or an unknown metal, and give them a sand to expose a fresh metal surface. Once they're sanded, you can dip each of the two metals into their respective metal ion solutions. We then connect the metal electrodes to the instrument using the alligator clips available, and lastly we need to connect up the two half cell solutions. We do that using a salt bridge. To use your salt bridge, start by taking it out of the potassium nitrate solution, give it a rinse down with distilled water. Don't force water from your wash bottle up the ends of the salt bridge. If you do that, you'll wash out the salt gel and your salt bridge will no longer be able to conduct electricity. Then you can lightly shake it off and place one end in each of the two half cells to complete your electrochemical circuit. You can then take a reading off the instrument. That reading will be in millivolts, so here I have an example of 0 millivolts, and then use that for the various questions you have in your report. In this experiment, you'll be investigating the effect of changing the concentration of one of the two solutions on the cell potential, and you're then going to use a cell potential measurement and combine that with theoretical half cell potentials in order to determine the identity of an unknown electrochemical half cell. So looking back over the prac, what can you do to make sure you come prepared for this experiment? First of all, make sure you've had a read of each of the 4 different theory sections for this experiment. So for your different reaction types and for your redox reactions. And then for each section, try and get started on some of the work before you arrive. Looking at the pH of salt solutions, the reactions that you need to write to describe these pH changes are reactions that we've already covered here in Chemistry 1. So there's every chance you could write most of those reactions prior to doing the experiment, and you can use your time in the lab to prove that you see what you expect to. For your flow diagram reactions, again, you can make a lot of predictions based on the solubility data, your KSP values, your formation constants, the KF values, and some of your simple known reactions that you've explored in the past, acid-base reactions and the like. For section C, when we're looking at the way that ligands interact with metals, there are some very common patterns and themes that run throughout the experiment. If you have a look again at the theoretical overview in this video, it should help you to start predicting what you might see for each of those reactions. And finally, for your redox section, there's space specifically set up for you to predict what you expect to see with your 6 test tube reactions, and you could also be set up and ready to calculate cell potentials and use the Nernst equation in order to calculate your non-standard cell potentials before you get to the lab. So make sure you do set aside a bit of time to pre-prepare for this prac. I think that's enough for now. Hope you enjoy it.